Hey everybody, this is a example video on substitution and indefinite integrals, and in this video I'm going to go through what we'll call creative examples, tricky, difficult, however you want to think about them. These are the problems that I'm going to go through in this video, so if there's a specific one that you want to see, you can just, fast forward to it. Or you could use this as a way to quiz yourself, and then if you're unsure, then you of course have all the explanations here, so decide what is the best way to use this video. Also, in this video, I am assuming that you already kind of understand substitution, and so I just kind of plow ahead with it without necessarily breaking everything down. If you are looking for a more detailed explanation of just how substitution works or how to approach problems like this, I do explain that in my lesson video. So example videos are more just plowing straight through examples, and then my lesson videos are more trying to break down actual technique. So just consider that if you're watching this and you're thinking I'm in over my head or I have no idea what she's talking about, maybe you just want to watch some of one of my other videos on just the detailed lesson. So starting with this first one. All right, so this is kind of like, I'm also going to walk you through kind of how I might go about this. So in general, when I look at this, so I'm thinking a little bit ahead here, and I'm always thinking about my u and my du. And I just kind of notice, so if I made my u x to the 6th, my du would be 6x to the 5th, and this doesn't really help me in this case. This is not going to be an easy substitution. So what that tells me is I've got to play around with this a little bit. Now, a rule of thumb is if you can break up the fraction into pieces, a lot of times you do want to do that. So I'm going to break this up just to see what I get. So this will become 1 over x to the 4th, and this will become 1 over x to the 5th. Now, as it stands, I still really can't use either one of these for a substitution. So if you're thinking about this, maybe you're saying, oh, but what about x to the negative 4th? Because then my du would be negative 4x to the negative 5th, and this won't work because while it's true that we do have this x to the negative 5th, I can't have my du fall in under the square root, so that would be a no-no. So what that tells me then is I don't have this quite where I need it to be, so I have to keep thinking creatively. So I'll get rid of all this. And so what else could I notice about just how this is being stated? Well, one other thing I notice in how this is written, I can actually factor this a little bit farther. Oops. So I can actually factor this a little bit farther. So how can I factor this? Well, I can factor out 1 over x to the 4th. So what does that leave me with? 1 over x. Okay. Now, as it stands, I still can't really do anything with this from a u-du standpoint. But what this helps me with is that I can actually evaluate this square root pretty easily, actually. So what I mean is I can take the square root of 1 over x to the 4th, and then I've still got this other square root. So I'm always allowed to break these up like this. This is an algebraic trick. And so then if I take the square root of this guy right here, this will equal, so I'll come up here, 1 over x squared times the square root of 1 minus 1 over x dx. And now we're actually in business. So notice now, if I make my u equal to 1 minus, let's call this x to the negative 1st, what would my du be? Well, then my du would be x to the negative 2nd dx, and wow, that just like totally cleans this up and makes this so much simpler. So my u is going to be this piece in here, and then my du is comprised of this and this. So this is actually nice and straightforward and no other manipulation required. So this just becomes u to the 1/2 du. So then I can integrate to get 2/3 u to the 3/2 plus c. And then I get 2/3 times 1 minus 1 over x to the 3/2 plus c, and I'm done. So this one didn't require much manipulation at this point, but we did have to get pretty creative up to this point. And this is, again, something that you just kind of figure out. Like, you just kind of keep thinking to yourself, what else could I try? What else could I throw at this? And you're constantly writing down u's and du's to see if anything works. Totally normal part of the process. Okay. Now for this example, this one's pretty tricky, I think. And I explained kind of other forms of this in my first explanation video. So if you struggle with kind of this explanation, like if it feels like it's too much, highly recommend you check out my longer explanation video just to get the basics of the technique, and then come back to this. So just a little bit of a warning here, because this one is pretty tricky, so you might need to kind of take it in steps. So first of all, what I want to do, just to make the problem a little bit easier to look at, I want to bring the 5 out so that I can just kind of focus on the rest of this. So this 5 is just going to be noise. Now, my u in this case is going to be 4x cubed plus 1. Therefore, my du is 12x squared dx. Now, looking at this right away, you can say, oh, but we have x to the 5th. And so here's where you've really got to start to get creative. So I can break up x to the 5th. So I'll just kind of note this. X to the 5th is the same as x cubed and x squared. And when you look at my u and my du, here's x cubed, here's x squared. So technically, I could actually rewrite x to the 5th and kind of break it up with this, and then kind of use these terms to like help me rewrite x to the 5th. So I'm going to do something a little unorthodox here just to make sense of this. But first, what I want to do in this first part, I want to just solve for x cubed. So if I solve for x cubed will equal, so I subtract the 1, and then I'll divide everything by 4. So this is going to be my x to the 3rd, okay? Now, the x squared here, so again, this is going to look a little strange, but this will help us kind of accomplish what we need to accomplish. So if I solve for my x squared here, this would be du over 12 dx. Okay, so now what I want to do is I want to take this piece up here. So my x to the 5th equals x to the 3rd, x squared. And now I basically want to replace it with these pieces here. So this is going to be u over 4 minus 1/4, and then du over 12 dx. So let me just simplify all of this. So I'm actually going to call this, let's see, if I multiply all this together, so I get 1 over 48u minus, let's see, 1 over 48. So there's the numbers part, and then all of that is still times du dx. So I had to play around with this a little bit to kind of get to this. But here's how I can replace actually my x to the 5th. So I've got my u, and now I've got my du, and I've also figured out what my x to the 5th is. So this is all kind of just a mess to look at here. Let me, just to kind of now round everything out, so I'm just going to summarize this. So we just said that x to the 5th equals, so 1 over 48u minus 1 over 48 du dx. So it's not uncommon to have to kind of mess around with some of the symbols a little bit to try to figure this out. So don't be surprised if you're just laying out tons and tons of algebra trying to see if you can cancel things out to make sense of it. So now, coming back to this piece here, basically now I'm going to make a few substitutions. So where I see an x to the 5th, I'm going to replace it with this stuff here. And then this was my u. So I'm just going to kind of see, actually, I'm going to start with those two. I know I've still got a dx here, but let's just make those substitutions and kind of see where we're at, and then see if there's anything else that I have to do to manipulate this, because it's like I've just got a lot of stuff going on here, and then this x to the 5th also came with like a du dx, and I'm getting a lot of signs. So I just want to kind of write everything down to figure out what I've got. So where I have this x to the 5th, so I'll write it in blue. So this is 1 over 48u minus 1 over 48. And then I had that du dx, so that is now my whole x to the 5th. And then this is times the square root of u. And then I still have this dx over here, okay? So I made a couple of these substitutions, and so now just look at what I've actually canceled out. So because of just the strange work that I did over here, messing around with x to the 5th, you'll notice now that these dx's actually cancel out. So that is just the consequence then of we were actually using, like, this du over here. So we were just kind of manipulating the x squared. You can kind of manipulate whatever you want over here to make the problem work, to make your dx drop out and your du drop out. So sometimes you might get creative with the algebra, and as long as you're kind of staying within your substitutions, you can still kind of make it work. Okay, so now let's see. This is going to be, if I rearrange this all now. So why don't I bring out let me bring the 48s out. So this 5 over 48. So this leaves me with u minus 1 times u to the 1/2 du. So that worked out, huh? And so now I can actually distribute this u to the 1/2 into the integral. So I'm running out of space here. So I'm actually, I'd highly recommend that you kind of write all of this detail down, because I'm going to get rid of it so that I can keep going with the problem. So now I just have my u and my du for reference. So now we can distribute. So this is 5 over 48, so I just brought that out. So this is now going to be u to the 3/2 minus u to the 1/2 du. And now it's like finally we can integrate here, right? So, and it actually turns out to be pretty simple, like a nice simple-ish integration. I won't call it totally simple. So this will be 5 over 48 times, so this will be 2/5 u to the 5/2 minus 2/3 u to the 3/2, all of that plus c. And so now I can just finish distributing the 5 over 48 and replace all my u's. So in the end, my answer will come out to 1 over 24 times 4x to the 3rd plus 1 times 5/2, or to the 5/2, plus 5 over 72, 4x, 4x to the 3rd plus 1, all of that plus c. And so now there's the answer finally. So kind of a lot of work for that one. So that one's tricky. Oops, and I almost forgot my 3/2. Okay, so that's that one. So like I said, if you just watch this and you're just like too much detail, I don't even get how you could bust out that technique or anything. This one's very, very difficult and requires a lot of creativity. So I have a longer explanation of a problem kind of similar to this, but it's not nearly as creative. So there's like a basic technique with this of solving for other letters. And once you kind of understand the basics of that, then you can kind of go to this nuclear example. So don't fret if you're like, oh, I didn't understand it. Okay, so let's keep going. Now for this example, this one's a little tricky, and actually doesn't technically require substitution, though you can use it. So part of just figuring this one out is figuring out what the heck you're even trying to make your integral as. So for this one, as a big hint, I'm going to show you just a list of antiderivative formulas for some of the inverse trig functions. And so what I notice about this is that this is something squared, this is something squared, this is something squared, it's all being added here. And that actually looks very similar to inverse tangent. So sometimes what you can do is you can manipulate certain integrals to kind of force them into a particular format. So ways to kind of just get rid of some of the noise here, take out the 7, and so here I am here, and now I look at this and I'm like, okay, but this is 4 plus 25x squared, and the problem is that this needs to be a 1, and then as long as this is squared, I'm good. So you can actually manipulate this now to force this to be 1. So if I want this to be a 1, what would I have to do? I would have to divide every part of this by 4. So I'm going to do that. I'm going to divide this by 4, I'm going to divide this by 4, and I'm going to divide this by 4. So then look at what I get. I get 7 over 4 times the integral of 1 over 1 plus 25 over 4x squared dx. Now, if you are really comfortable with your antiderivative formulas, there actually is a formula just for this, for what to do with this k squared. So some people are comfortable with this, and then other people prefer using substitution. So I'm going to just show you how to use substitution with this, but you totally could have plowed ahead with this without using substitution. So Now, basically, what I'm going to do is I'm going to notice that I can rewrite this one more time as 1 over 1 plus 5 over 2x squared. And now I can make my substitution. So in this case now, my u is going to be 5 over 2x. Therefore, my du is 5 over 2 dx. Therefore, my dx is going to equal the reciprocal 2 over 5 du. So now I can make some substitutions. So this will give me now 7 over 4 times the integral of 1 over, so this becomes 1 plus u squared, and then 2/5 du. So now I want to multiply this 2/5 by this 7 over 4. So if I do that, I get, so let's see, I will get 7 over 10. And this whole integral here, now that's just cookie cutter formula, right? That's really just inverse tangent. We don't even have to really think about it that much. So this becomes 7/10, inverse tangent of u plus c. Now I just have to replace this with what I originally had. So this is 7/10 inverse tangent of 5 over 2x plus c, and boom, we're good to go on that one. So that one, maybe you had to use substitution, maybe not, but this is kind of a common one to come up, and it is, you still have to kind of manipulate and get a little creative with it, and sometimes people get a little thrown off because it takes a second to wrap your head around that it actually is inverse tangent. Okay, so hopefully you have this list next to you because we're going to use it again for this next one. Okay, now this problem is going to require some serious creativity, okay? So if we kind of start playing around with this, so if I were to say, oh, x to the 4th minus 1 should be my u, of course I can see, okay, so this is not going to work because I don't have 4x cubed. But the problem with this problem is that I also really can't manipulate this 4x cubed, or sorry, I cannot manipulate this x here. I can't manipulate this to make it look like x cubed. So this is a little bit different from this crazy monstrosity of an example that we did just a few minutes ago, where, you know, this exponent was higher and I could actually kind of manipulate this to be a combination of the u and the du to make this work. I don't have that option here because I can't really break up the x to make this work. So there's going to be some further manipulation needed. So it doesn't make sense to make x to the 4th minus 1 my u, nor does it make sense then to make the x my u. So now it's kind of like you have to start thinking of what even should you be trying to make this look like. So this is where having your antiderivative formulas in front of you can be really helpful. So as you look through this list, what does this kind of look like? Not really, but sort of. It kind of looks like this, right? And so we're going to say, all right, maybe I can manipulate this in such a way to make this work. So that's kind of the driving thing. So as I look at this, what I think to myself is, okay, this is x to the 4th. That's not what I need. Is there some way that I could manipulate this to actually rewrite this in a way that I'd like? So there is, right? So I could rewrite this as, so maybe I'll just kind of show you the integral. So let's bring the 3 out too, by the way. We don't really need the 3. 3. Okay, so this is now 1 over x times the square root. So this is x squared minus 1 dx. And I'll try not to write so slanted up. It's kind of hard sometimes. Okay, so from here, all right, so my u could be actually 2x, right? Because if, or not, I'm having all kinds of problems. My u could be x squared, because then this would allow me to have u squared minus 1 under here, right? Which is closer to the format of this antiderivative. So this is kind of my target. Now the problem is, when I do my du, I get 2x dx. Why is this a problem? It's a problem because this x is in the numerator versus this x is in the denominator. So this x is not in the right spot. So that doesn't mean that I did something wrong, but I do have to keep getting creative. So what I would like to have happen, this can be like a way you can think through problems. You think of what would you like? I would really like it if I had an x in the numerator, right? If I had an x in the numerator, I would at least have my du. So how do I get an x in the numerator? Well, what I could do is I could multiply the top and the bottom both by x. So let's just see what that gives us, and maybe that will get us where we need. So, you know, sometimes it's like you don't know what it's going to do. You're on a little bit of a journey here. So, okay, so I've got all this, and then this was x squared minus 1, and then all this was dx. Okay, so take a good hard look at this for a moment. So now, as I look through this, I've got my x dx, so there's my x dx. Now what about my u's? Well, the strange thing that happened when I multiplied the top and bottom by x, this turned this into x squared. Is that okay in this case? It is, because I've got the u over here. So this actually can now be replaced by u, whereas a moment ago it couldn't. And then this can also be replaced by u. So we might actually be in business here. So now, maybe the last thing that I want to do here is just, I'll solve this for dx. I know this is kind of a popular approach, so I usually just plow through like this, but I'll solve for dx. So I have my dx will equal du over 2x. So I'll write it like that. So let's make these replacements now. So the 3 is still hanging out here. So I'm leaving this x up here. This is going to be u. So x squared becomes u. And then under this, the radical, this becomes u squared minus 1. And then where I have this dx, I'm going to replace it with this du over 2x. Du over 2x. So now let's see, what can I actually cancel out here? So I can cancel out this x with this x. So then I'm just left with this 2. So I can bring this 2 out in front. So this will now be 3 over 2. Okay, so let me erase all this, and now let's keep going. So now I've got this 3 over 2, 1 over u times the square root of u squared minus 1 du. And oh my god, totally works. Ah, so great. So I really like this problem. I think it's just so clever. Okay, so now this is like very straightforward to finish, right? At least for taking this antiderivative. So this is inverse secant of u. So now at least that part was nice to do. And now I just replace my u with x squared, and I am done. So that's it for that one. So very creative thinking. Like I said, a big part of what can help you with this is thinking about what you would like to have happen, and then just seeing if you can manipulate the problem to make that happen. Sometimes it works, sometimes it doesn't. Doesn't mean you did anything wrong either. It's totally normal. We all go through it. So that's it for this video. So hopefully this was helpful. Like I said, if you're looking for a more detailed explanation, I do have a whole breakdown of kind of how to approach these problems. Hopefully you found this helpful, and hopefully I'll see you guys next time. Thanks for watching.